Look, it's our old friend, the hydrogen discharge lamp. So we've seen this a number of times over the course of the quarter. I've got some hydrogen in a tube, and I'm beating it up with electricity. And now, finally, what we're going to do is explain why you see this. So I take diffraction grating, and I break this purple light up into its constituent colors, and I see that there are really only a couple of them. So this purple is actually a mixture of, there's definitely a red, I see a bit of a green, kind of a teal, blue-green. If I looked really closely, I would also see deep indigo and actually a pretty light violet as well. So what's going on with this? And in fact, I could also give you at least one hint is, and you are so lucky, we have a deuterium tube. So deuterium is hydrogen, but it's got an extra proton. And if I looked at the deuterium lines, it's weaker because it's expensive and old. I would actually see that to within maybe 1%, they show up in the exact same places. So there's something in here that tells us basically about the number of protons and number of protons and electrons. So a little bit of a side trip, and of course we won't talk about this in full detail for the reasons discussed in the last video, is that we're going to talk a little bit about quantum mechanics, namely the wave-particle duality, de Broglie's hypothesis, which is a more mathematical statement of the whole wave-particle duality, and atomic spectra, namely why do they have those specific lines, and can we predict anything quantitative about it? Okay, so first, wave-particle duality. Sometimes matter acts like a particle. That's been all of 1050, your mechanics class. Sometimes it acts like a wave. That'll be this last week in 1070. And you really only care under a certain circumstance, and that's what de Broglie's hypothesis says. Actually, this guy, Prince Louis de Broglie, said that the wavelength of matter, so if I have some particle of matter that has mass m, is given by this, h over p. Got a PhD for that. My PhD was like 110 pages before the appendix. This was his, so good for him. But basically, the reason you guys mostly don't care about matter as a wave and usually as a particle, as we'll crunch through some numbers, and the wavelength of matter is typically like super, super small, much less than human natural perception, and much less than you usually care about. And this is basically the same issue with light acting as a particle, like a ray diagram would suggest, and a wave, is that honestly the wavelength is so small you usually don't care about it for all but certain phenomenon. Okay, so we'll get a little bit into that, and then again, atomic spectra. And we'll talk about numbers for hydrogen-like systems. So a hydrogen-like system might be helium, but with one of its 2 electrons removed. So first, let's talk about de Broglie's amazing formula that he got an incredible amount of credit for. And let's just ask, what is the wavelength of what you actually probably through this whole class considered to be a particle? And we'll do a molecule of nitrogen at STP. So essentially a molecule of air. And so that is lambda. I got to know what h is. H is this thing called Planck's constant. And that's the entire branch of the wave-particle duality that we won't talk about, which is what kind of broke this whole thing open in the first place, is essentially this ultraviolet catastrophe in thermal physics. Like, why wouldn't a hot thing just immediately radiate the smallest amplitude, smallest wavelength radiation and just immediately give up all its thermal motion. So Planck figured out that radiation was quantized. So radiation acts like a particle. We want to talk about the other part of this, which is when matter acts like a wave. But anyway, Planck's constant in SI units is 6.626 times 10 to the minus 34th. It's really tiny, joule seconds, or joules per hertz. And so what I got to do is figure out what the momentum, so this is P for momentum, is for air at STP. And fortunately, you guys figured that out probably like twice, 2 or 3 times, either pencil and paper or by using some Maxwell-Boltzmann distribution applets. So we've got to figure out the mass of nitrogen. Nitrogen is 28 grams per mole, so I'll divide that by the number of particles in a mole. And I get that one molecule of nitrogen is 4.65 times 10 to the minus 23 grams. Let's turn that into kilograms because we want to do SI. So 4.65 times 10 to the 26 kilograms. The other way of doing that is to count up and know that each proton or neutron is about 1.67 times 10 to the minus 27 kilograms, multiply it by 28, you'd get the same answer. And then what I need to know is how fast is air moving at STP. And you guys got that that's about 400 meters per second. I don't think more sig figs than 1 is necessary. SI units, SI units. Therefore, what we have is the wavelength of nitrogen in air is Planck's constant, 6.626 times 10 to the minus 34th. Joule, okay, wrote the divided by, so I'll do joule per hertz. You'll maybe understand one day why that's the cooler way of writing it. And then mass is 4.65 times 10 to the minus 26th kilograms, and then 400 meters per second. And we get a crazy small number, 3.6 times 10 to the minus 14th meters. Okay, so this is why it's okay to treat air, molecules, nitrogen, as particles and not waves. So essentially, you know, if you look at this thing whizzing along, you've got to zoom in so far before essentially what you're seeing is the wavelength of this packet, so this kind of probability packet of the particle going through. These are the philosophical details of the wave-particle duality. But imagine that you've got this kind of like sound wave, you know. Think about an entire like wave file if you know, the whole song, and then you zoom out and you zoom out and you zoom out, and at some point it just looks like a blob. So this is an incredible amount of zooming out to do to get from 10 to the minus 14th meters to 1 meter, right? Like a box of air. So we usually don't worry about this until now. Now we really do, because now we're talking about this small particle, in fact an electron, spinning about a positively charged nucleus. So maybe those are more relevant numbers. And as you can see from the de Broglie formula, the smaller the mass and the smaller the speed, the bigger the wavelength. So let's just like go really nuts and let's look at the wavelength of an electron going at 1 meter per second. And to make that more dramatic, I'll write one single electron. So lambda is Planck's constant over the momentum. That's 6.626 times 10 to the minus 34th joule seconds. Okay, mass of the electron is 9.11 times 10 to the minus 31st kilograms. It's teeny tiny, so that's going to make this wavelength pretty big. And we said 1 meter per second just to make the math easier. And what we still get is like 7 times 10 to the minus 4th meters. So about the size of a human hair. And good luck to you getting an electron down to 1 meter per second. So, this is about as good as we're going to do, just kind of without really advanced technology. You actually would need it to get 1 meter per second electron. And this still is, this is the width of a human hair or something. So the quantum mechanical world is basically like kind of inaccessible. So what we're going to do is use this idea, the idea that matter has a wavelength and is a wave phenomenon, to explain the non-collapse of atoms and this weird chunky quantization of the spectra of atoms. So there was this guy, so the story goes, who said, I'm really good at figuring out, give me a bunch of numbers and I'll tell you what formula they came from. And somebody challenged him with the wavelengths of light from the hydrogen spectrum, the frequencies or wavelengths that you guys saw. And sure enough, he found the structure. So there is mathematical structure in those lines. And the structure looks like this. There is one constant in those kind of random seeming lines. You really just need to know one thing. And this thing R is called the Rydberg constant. You'll see it in centimeters in older textbooks, but I like meters. And these are integers. So m is actually an integer, positive integer. And the easiest way of writing the relationship in between m and n is to say that n's got to be bigger than n. So we can't have a negative wavelength, essentially. So, if this is 3, this would have to be 4, 5, 6, 7, 8, 9, 10, 147. If this was 6, this could be 7, 8, 9, 10, 147, 5,743, whatever, all the way up to infinity. So you pick an n starting at pick an m starting at 1, and then n has got to be bigger and bigger and bigger still. So whatever you've got to do to make this positive. And I'm wondering if I didn't say that exactly backwards. Because this is in a denominator, n's got to be greater than m. So that statement's correct, regardless of what I said. So let's just try this. And again, this is an empirical formula for now. Turns out we're going to sort of derive it. So let's use the Rydberg formula for, I don't know, 2 and 3 or something. Let's do m equals 2. So we've got 1 over 2 squared minus 1 over 3 squared. And Rydberg constant is that. And so I have 1/4 minus 1/9, and then I pull out a calculator, and I get 1 over lambda is 1.5236111, 1 over meters. That's kind of goofy. So let me flip that. I'll take the reciprocal of that, and lo and behold, I get 6.56 times 10 to the minus 7 meters, or 656 nanometers. And that's that warm red line that actually showed up in the hydrogen spectrum. So it turns out that the visible spectrum of hydrogen is essentially like m equals 2. So m equals 3 and 1 are infrared and ultraviolet, and we'll again puzzle all of that out. So the ideas that go into the Bohr model are as follows. Quantum mechanics is a thing, so I have electrons and protons and neutrons for that matter, but that's less important, that have a wave nature to them, and their wavelength is given by the de Broglie wavelength, essentially. And so I can figure out what that is, and that's going to be something on the order of, 10 to the minus 10, something like that, so some tiny number. And then I also have this atomic model that we talked about in the slides in the last video. So I have 2 ingredients. I have an atomic structure model, and it's kind of planetary, where I have some positively charged protons and some neutral neutrons who are just kind of along for the ride for us, and then I have a cloud of electrons which are outside of them. I absolutely hate writing this, but it's kind of true. So something like this. And that in and of itself can't quite work. Because again, the electrons would radiate all their energy and fall into the center of fall into the nucleus. But I also have quantum mechanics. Which in this case, maybe the historical name would be a bit better, wave mechanics. And specifically, electrons would have a wavelength given by h over p. So if you combine these 2 ideas, you essentially get the Bohr model of the atom, which has the positively charged nucleus. And this is so hard to draw, but give me a little bit of squinting and assistance, is that they're standing waves in the same way that they're standing waves in, again, like the musical tone of an instrument. And I have 0 nodes, 1 node, 2 nodes, and I can only have certain allowed wavelengths of electron waves surrounding the central positively charged nucleus. So the important part is that there are only certain places where the electron can be. So this is not a planetary model in the sense that we have one, where I could take Mars, and if I gave it the right amount of kinetic energy, Mars could be a little bit farther out, or Earth could be a little bit closer in if we lost some kinetic energy. Not true. Because of the wave nature of the matter, there are only certain allowed orbitals. And we'll come up with the condition for that, essentially dumping de Broglie's hypothesis in. But first, let's go through a planetary model and then change what needs to be changed. So pure classical planetary model would look something like this. And this is kind of a review of the relevant electromagnetic physics. I've got a nucleus And let's just do hydrogen. Got a nucleus. That nucleus is a proton. And then I've got, heaven help me, this little green ball of an electron over there. And they're separated by this distance that we'll call A. It's called the Bohr radius. I'll just call it A because it's got to be called something. And it's scooting around like a planet around the star with some velocity v, which is tangential. And it's executing uniform circular motion. So F equals ma. The force that's holding them together is the electrostatic attraction because they're separated by some distance a. That's negative, that's positive. So that would be 1 over 4 pi epsilon naught q, so the charge of the proton, the charge of the electron, I'll fill these in a second, divided by a squared. So that's the electrostatic attraction in between them. The mass that we care about is the mass of the electron. I'll put that in a second. And then that's v squared over r. R is a. Okay, so that's the centripetal term, v squared over r. It's the mass, and then that's the actual force. So then I'm going to start just kind of shuffling what needs to be shuffled. So usually what we do is we call 1 over 4 pi epsilon naught k. I'll do that just to clean stuff up, so defining that usual constant. And then I'll note that both of these are the fundamental charge, so those are both e, so I get an e squared. And then I'll just solve this for a in a second and point out that that's the mass of the electron. And then yeah, we'll leave v itself for now. Actually, let's do this right now. So this is mv times v. Okay, hopefully you followed that derivation. And what mv times v is p squared over m. So that's 1p, and that's almost another p. I just would need to put a mass upstairs and in compensation downstairs. Okay, so what I have is classically, I have this idea of the distance in between them would be given by the momentum, mass, and the fundamental charge. So I would have A is equal to, sorry, you got the K there. A would be equal to K me e squared over p squared. So that is a completely classical treatment of the hydrogen atom as an electrostatic attractive system. So now what I'm going to do is do what Bohr and therefore and de Broglie did, is I'm going to put in quantum. And the quantum hypothesis, in some sense, is that I can only be in certain allowed orbitals. And those orbitals are, this n might change later, so n just stands for generic integer. This isn't the Rydberg integer necessarily. N lambda equals to 2 pi a. Right? So we have standing waves, and we can have a full wavelength, we can have 2 full wavelengths, we can have 3 full wavelengths. Tried to draw it here, full wavelength, 2 full wavelengths. Forgive me, it's kind of hard to draw circular standing waves. But this is essentially the quantum hypothesis. And we can just dump that in right there because we've already worked out the relevant classical physics. So I have, using star, and a little bit of math, I would end up with K yeah, I think this is the best way of writing it. KME squared over H. Sorry, let me do this backwards, actually. So remember that for 1 second. Let's put in de Broglie first. So we need this, the quantization around the central atom, but then we also need the idea that what is the wavelength in the first place? And the wavelength in the first place is, according to de Broglie, h over p. So let's do that first and take star and change p into h over lambda. So we have k me e squared, and then p squared would then become h squared divided by lambda squared. So we'd have an h squared there and a lambda squared there. Okay, so Bohr radius, and now what we have is this would be the quantum mechanical momentum. Now we're going to put in the quantization condition. So this is what's known as the Bohr quantization condition. And finally, we would have A equals, I'm just going to call this R sub n, undoing our k that we used for a bit. Actually, we'll leave it, because that's gross enough. So these would be the radii of the electron orbits. So n can only be an integer. N would be 1, 2, 3, ... And these are the only places where you would expect to see an electron in the Bohr model. So it's not quite true. If you know stuff about like p and d orbitals, there's not one single defined radii for those. This is only the Bohr model, and it's not a great model outside of hydrogen. And we can kind of nix A. And then we can ask the more important question is, what's true about the energy itself?